Hello, everyone. Thank you for coming today. Today we're going to discuss different ways of making remote calls in distributed systems.
Wait a second. Let's start with what makes us qualified to even talk about this. I'm Mykyta Protsenko. I'm a hands-on engineer from Roku. And during my career, I worked on a number of different projects using both monolith and microservices architectures. And today, I'm going to describe how to avoid common pitfalls while using REST.
It's pretty easy. Don't use REST to avoid these pitfalls. And I will tell you what you can use instead and why. My name is Alex. I'm a software engineer. I've been building systems using REST, using SOAP, using different RPC solutions. Currently, I work at Google, where I started to use gRPC. So today, I'm going to tell you why gRPC is one of the best choices you have when it comes to remote calls. I'm also a member of Devoxx Ukraine program committee, and Devoxx family is expanding, and Devoxx Ukraine is happening this November. It will be first edition of Devoxx Ukraine. If you have something interesting to share, so please talk to me or submit your talk. If you want to attend it, it can be a great idea as well. We will have amazing talks on Java, on building systems, on gRPC and other topics. But today we are comparing gRPC and REST, so let's start.
Let's start from the beginning. Very often, when people talk about REST, they use a lot of big words. Hypermedia, self-descriptive resources, service-oriented architecture. But let's start with what REST is not. REST is not JSON over HTTP. Very often, people get confused, and they mixed up HTTP APIs and REST APIs. Even Roy Fielding, the author of the REST concept itself, is pissed off about this confusion. So let's unconfuse things. Let's learn how to tell HTTP APIs apart from REST APIs. If I want to describe REST in 2 words, these 2 words would be?
Something ancient.
No, architectural pattern. A set of concepts and practices to make your system more scalable and your life easier. And the most important of these practices is state transfer. What does it mean? It means the client has all the data, all the state of the current session, and if it wants to change the state, it transfers the changes from client to server, and the server is 100% stateless. Why is that important? Let's take a look here. On the left, we have an example of a good RESTful API. We have a resource that has a unique identifier, some state. A client can call the server using this identifier, fetch the state, change the state, send the changes back to the server. These kind of systems are easy to write, easy to scale, easy to maintain. And on the right, we have an example of anti-RESTful API, where the server has to keep the state of the current session, and it smells of sticky connections, of scalability issues, and of weird bugs.
There is no REST for Zipkin. OK, so we understood what REST is not, and now let's learn what is gRPC. Google started to use microservices a long time ago, probably even before this term was invented in the industry. And as we all know that in microservice universe, every client call results in 100 remote calls. So to make all this inter-process communication efficient, Google developed some framework for remote procedure calls, or RPCs, and it was called Stubby. So Stubby was used inside Google for many, many years. And finally, a few years ago, Google open-sourced a new generation of Stubby called gRPC. So gRPC is a high-performance RPC framework originally developed by Google. Now it's a part of Cloud Native Computing Foundation. It uses HTTP2 as a network protocol. And it's built with all the modern requirements to distributed systems in mind. And if you are wondering what G stands for different things every single release.
Well, G is good, but you said these 3 words, RPC, remote procedure call. What does it mean? Back to the age of Corba and RMI?
Nice try. But no, gRPC is neither Corba nor RMI. Please remember that and never, ever compare them. Because gRPC is built with all the lessons learned by years of using Stubby. Lessons in scalability, in performance, in building a tool which is easy to use and easy to maintain for a long time. We can even say that gRPC is more than a library. First of all, there is a set of best practices, of principles, how to design your distributed systems. And gRPC is built on top of them. Out of the box, it provides you default implementations for all these abstractions, but it also gives you extension points. And using these extension points, you can customize it, you can plug in your changes, you can add new features, and so on. And today, gRPC is not only Google. There is an ecosystem around it, and there are other companies and individual developers who contribute to its ecosystem. And what makes it even more popular, that it supports more than 10 programming languages, including JavaScript, since gRPC Web was open sourced in beta just a few weeks ago. So it gives us freedom and flexibility. We can write prototype of our service in Python and then rewrite it for production in Java, for example, and for our clients it will be transparent. And now we can have our entire stack built in gRPC from backend services to clients, mobile clients, and web clients.
Wait a second, you're talking about implementations now. But is it even OK to compare gRPC and REST? Because obviously gRPC is library with some concrete implementations, and REST is an architectural pattern.
Sure, yeah, it's a good point. But again, gRPC is more than libraries. Think of it as a set of best practices is built on. And de facto, both gRPC and REST are used for remote calls in distributed systems, including microservice architectures. And let's recall how we are usually taught to build our microservice architectures. It's pretty similar to drawing an owl. They tell us, take our framework, XYZ. Now it's whatever, now it's reactive, it's easier. And then just add your microservices.
But the truth is rarely true and never simple.
Absolutely, because it's 2018, and we all know that with microservices we solved one problem and acquired new ones. Let's rename, let's recall some of the challenges we are facing now. Now we have the services that call other services, and they call more and more and more. So as a result, we have this complex call hierarchy and huge amount of remote calls. And first off, it's going to affect our performance because all these calls are more expensive than in-process ones. But we have a few more problems, at least. First of all, before we make this call, we have to find service to call. Right? We have to discover service, so we have to solve the problem of service discovery. And in production and practice, we always have multiple instances of the same service for scalability. Right? So at every given moment in time, we have to find out what instance to call, depending on load or some other metric. So we have to solve load balancing as well. And after we solve this, we made our calls. And now we need to monitor all this call flow. And when some services are slow, we have to be able to find them and tolerate them.
It's even worse than that, because services won't just be slow. They will die. They will crash and burn. As Leslie Lamport said in 1987, a distributed system is the system where your computer may break because of a computer you didn't even know about, or something like that.
1987 was even before people started to use REST, or about
way before. But the point is, we need to learn how to deal with the systems, with the services that die and crash, how to make sure that the rest of the system keeps running.
OK, so as we see, with microservices, we have a lot of new challenges, but we're lucky because gRPC is built with all these issues in mind, and it helps us to approach them.
Oh, well, not only gRPC, REST got introduced back in the year 2000, and since then people have learned how to deal with these challenges there as well.
Did they?
They did indeed. So let's take a look. Let's actually go ahead and write a sample service. What does your service usually do when people call it? Usually it executes some logic, and it calls other services. So let's write a service that will call other services. Let's write a content aggregator, for example. And what are we going to use for the list? For the content sources, maybe a list of Pokemons?
Or big data buzzwords?
Big data is so 2017. Let's use a list of cryptocurrencies. It's where all the hype is now. So let's actually take a look and see how can we design a RESTful architecture using a Spring Boot application.
But I thought they could return data in different formats,
yes.
Right?
Yeah, they totally can return data in different format, and some of them will return data in binary format, some will return data in JSON, and some will use XML.
Because XML and REST are like two peas in a pod, right?
Actually not. REST is totally format independent. You can use homing pigeons for a transport protocol if you want. And to illustrate that, we are going to write our sample Spring Boot application to return a client a response in a unified format. So let's actually go ahead and see what we are dealing with. Similarly to a classical web application, we are going to have a controller to handle a request and a response. We're going to have a service to encapsulate our business logic, and we're going to have a data layer to call our external content sources, and these content sources will provide us resources first and foremost. And these resources are going to have unique identifiers so we can find them, and they're going to have some structured data. And the format of the data, XML or JSON, is actually irrelevant. Why is that? Let's take a look. Modern frameworks can handle the issues of serializations and deserializations for you transparently. You don't have to worry about this. It's just as easy as drawing circles instead of an owl. The fun part is going to happen in the service. The service is what is going to aggregate the content, execute some logic, and return us this aggregated content back. And what are we going to have here? First of all, we're going to have an identifier so we can find our content somehow. We are going to have the actual content like Pikachu or Bitcoin. And we're also going to add value. Tell it this is a Pokemon or big data. And finally, we're going to provide a next ID so we know how to find the next item. So finally, we just need to add a controller to delegate a call to the service, and we define our URI, resource identifier, and the response format, which is JSON in our case. So this is it. Modern frameworks gives us a system that is easy to integrate with, because all modern languages have production-ready HTTP clients, and you can even use curl to test your system to see if it's even working.
Sure, but to use curl or HTTP clients, I need to know what instance to call again, right? Where to find your service. How do I solve this problem in REST world?
That's a great question. So let's take a look how can we solve a problem of service discovery in REST universe. Today we have a bunch of solutions on the market, starting with the world-famous Apache Zookeeper. And many of these solutions actually use DNS-based approach, resolving a DNS record to an actual instance. And let's take a look how it works in Kubernetes, for example. So we have two Kubernetes services defined here, and one of the services is defining their name, and the other is using this name as a host name in the URL. It doesn't get easier than that.
OK, so you wrote your podges, your annotations, whatever, and they're easy indeed, right? And we're software engineers, we're developers, we love coding.
We do.
That's what we do, right? So we jumped right in our controllers right away. What do we often end up with? Very often we have a situation when we have several services, but nobody really knows their APIs. Mykyta, what is an API for a service?
Well, it's super easy to check. Let me just open my laptop and take a look at my control. Wait a second. While I was on vacation, Peter has changed something here, so I need 2 more minutes to look it up. Wait a second.
Does it look familiar to you? And it kind of worked when I had like 2 or 3 services, but in microservice universe we have gazillion of APIs, and it would be nice to have a way to formally describe them all.
Well, what stops us from using Swagger, for example? We can use Swagger IDL to describe our APIs, or we can go the other way. We can actually generate the Swagger IDL from our controllers and annotations.
Yeah, we can go one way or another way. Some of my services can generate, some other services can just use it, and like other services cannot use it at all. So it's inconsistent, and requires an additional discipline, it requires an external tooling. So with gRPC, we change the game. With gRPC, we start with an API. When we want to write a service that aggregates data from different sources, the very first thing we have to write its service definition or its API description. Out of the box, gRPC uses protobuf 3 as a language to define API. By the way, we can change this implementation, but let's focus on the default one. So with protobuf 3, we just describe our aggregation service. We describe RPC method get. It takes request. It returns response. In request, we have ID. In response, we have ID, response time, content, and ID of the next item. So that's it. So what we have now, we have formally described API of our service. We haven't even started to write any Java or whatever code, but we already have formal API description. And remember, I brought up a point that gRPC is built on best practices. So API first, having API description before coding is one of them. And all of my clients will just use this API as a source of truth. Now I take this service definition and generate classes from it. To generate classes from it, we use gRPC runtime. In case of Java, it will be gRPC Java runtime. With gRPC Java, we can do it from command line, or we can use plugins for our build systems. There are plugins available for Gradle, for Maven, for Bazel. So let's call our wizard gRPC runtime, gRPC Java runtime, and whoosh, and we generate abstract service. Then whoosh, and we generate request, response, and builders for them. Podges, we don't need no stinking podges.
But the client has to generate those builders now, right?
Of course, but it's just an extra step in your build process. It's super easy. And of course, we can, and we will generate client libraries or stubs. In gRPC, you don't need to write client libraries manually because nobody likes it. And now let's go ahead and implement service. So we have to extend our generated abstract class, and it already has a method get in it. This method, it's the same method we described in our IDL. So this method takes a request, but it returns void, you see, so it doesn't return anything. Why is that? Because gRPC APIs are asynchronous by default. Because when we receive a request, often we don't have a response right away, right? We have to call external systems, we have to call some data sources, or we have to calculate response somehow. So what can we do if we don't have a response right away? Of course, we can block the current thread, right? And but what happens when we block the current thread? Let's take a look at this example. We have a service that has a thread pool of size X, and it blocks thread per request. So when request arrives, it blocks the thread, and second, and third, and X. And then when X+1 request arrives, if all of these requests are still on flight, and if we haven't returned any responses for them, we have no threads to handle this new request, so we just reject it. So this approach it kind of works, but it doesn't scale. So that's why gRPC takes stream observer as a second argument, and stream observer is one of the key interfaces in gRPC. It has this method onNext. So you use this method when you want to send a response to your client, and it doesn't have to be from the same thread. So now, when my client calls my method get, I don't block the thread, I return execution immediately. And now I can receive more requests than I have threads in my thread pool. This approach is always called Hollywood principle. Don't call us, we will call you when we have something to tell you. And when we have a response for the first client, we will call him using method onNext. Then we call third, we call X, whatever response is ready right now. If we have a response right away, we can, of course, return it from the same execution thread. We build it with aggregation response builder. We set ID, content, type, and call this method onNext, providing response to our client.
Wait a second. I remember in your protobuf you defined a next ID field, but I don't see you using it actually here. It's missing.
Right. It's missing because I don't have it. We are talking about like stream of cryptocurrency, right? To have ID of the next item, I have to wait for the next item to provide the current item, right? But I want to return like brand new cryptocurrency to my client right away, so they can invest in it without waiting for the next one.
But how does your client know how to find the next item, where to find it?
Let's see. So I need this next ID so my client can send it back to me in the next request, right? So if I remove it from the request, I can remove next ID from the response. Super easy, right? So I just want my client to subscribe to my list of items, and I will return them new Pokemon or cryptocurrency when I have it. So that's a typical streaming scenario. While streaming, we have no IDs, we have just like one request and like many responses. So in gRPC, we can just add stream modifier to the response, and voila, we have server streaming API. Now my client can receive many responses on the same request. We have to probably rename this method now. It's not get, it's subscribe. And what we've got here, it's a new API. It doesn't have ID in the request, it doesn't have next ID in the response, and it's like clean server streaming API. Right?
Yeah, much easier.
Okay, but that was an aggregator says definition. But it takes data from external services, from content providers. So let's describe these content providers. Their APIs are even easier. So it has one method subscribe. Request doesn't have any fields. Response has ID and content. And we are going to have like different services. One service will return Pokemons, and another service will return cryptocurrencies. But they both will be described by the same API. And my aggregation service will call this content services using generated client libraries or stubs. So let's go ahead and implement aggregation service. So we will see how to first implement service streaming gRPC server, and second, how to use client libraries or stubs. So we take the stubs, we inject them in the constructor, and then in our method subscribe, when our client calls subscribe, we receive this call here. What we are doing here, we are doing fan out. We're doing just all the stubs for each stub subscribe. We're using the very same Hollywood principle on the client side here. So we subscribe to all our services from the very same execution thread, and we just return execution. So when we are doing subscribe, it's like, or RPC call in gRPC, it's like a voicemail. We just tell our client, please call me back when you have result for me, and here's my number, meaning my stream observer, with my method on next in it, and my client will send me back response when it has it. So my server, sorry, my source of the data. And when I receive this data, this method onCalled will be called, onNext will be called. It will be called from a different thread, of course. And what I do here, I just convert it to aggregation response using generated builder and send it back to my client. That's it. Right? So let's recall what we did. When my client subscribes to my aggregation service, it subscribes to all the content sources. When any of the source returns me some response, I return it back to my client, and so on. So to launch everything we wrote, we have to start gRPC server. Any idea how do we start gRPC server?
Maybe using annotations?
No, we use builders again, so gRPC is very consistent in using builders, at least gRPC Java. So we use native server builder, we set up a port, and we add a service that we just implemented and call start. If my gRPC server implements multiple APIs, which is usually the case, I can call add service many, many times. So Crypto client and Pokemon client are injected in aggregation service, so let's see how we created them. To create them, we use native channel builder. For host and port, we instantiated channel. And channel in gRPC is a logical connection between your client and your service. It's not physical connection, it's logical connection. Using this channel, we can instantiate client libraries or stubs. With method new stub, we instantiate asynchronous client. We already saw how to use it. It takes request and stream observer of the responses, and it doesn't block the current thread. If by some reason you need to block the current thread, you can use blocking client. There is an API available. And if you still want to be asynchronous, but you like more like functional style, future-based style, you can use future stubs. And on RPC call, it will give you back your future.
And what do you do with your future?
It's up to you what to do with the future. You can subscribe to it, you can map it to another future, you can collect multiple futures, and so on.
Well, sounds like a lot to choose from.
Actually, it's not that bad, because in most of the cases, like almost always, you will only use one of these clients. You have to choose what works better for you.
Well, that's still a lot to digest, but still it's a very beginning, like basics of implementations. And a while ago, you asked me about service discovery in the REST world, and now it's my turn to be curious. I wonder, how do you do service discovery in gRPC universe?
Sure. I mean, first off, nothing stops me from using the very same DNS-based approach. Here I did exactly that. And but gRPC doesn't limit me to using DNS-based solution. I can just like drop host and port and implement two interfaces, right? One is name resolver, is my service discovery tool, and another is load balancer, is my load balancing strategy. And if I have some custom client-side load balancing, for example, any other system I want to integrate, I can use it. So I can just implement my own load balancer, for example, and it will tell me what instance to call depending on some metric.
Like the phase of the moon.
Right, yeah, like the phase of the moon. And another thing to note here is Nady. So gRPC Java implementation is built on Nady, and Nady provides us an asynchronous and non-blocking I/O. And Nady uses HTTP2, and together with wire efficient protobuf, everything together gives us a high-performance framework. And performance is a first-class citizen in gRPC. gRPC team continuously running performance benchmarks. If you follow a link on this slide, you can find real-time performance benchmarks for the latest available release and for the latest development version and master. So these benchmarks run for every single pull request, so gRPC team is able to find any performance regressions as soon as possible, and we gRPC users can know what throughput and latency we can achieve using gRPC. So as you can see on the slide, for gRPC Java, for the scenario under test, of course, we can achieve more than 600,000 QPS if we use 8-core machines, or even more than 2 million QPS on 32-core VMs.
Well, you got me totally convinced. Non-blocking I/O is the way to go. But first, let's remember that you can do non-blocking I/O in REST universe as well. After all, asynchronous servers have been around for a while. And second, you are talking about streaming scenarios between services in the backend world. But what about clients?
Why is the problem? I mean, gRPC can generate clients. It can generate mobile clients. It can generate JavaScript clients. Since gRPC Web was open sourced in late March.
Well, let's take a look at the problem. Like, the problem is latency. What if you have a client in, let's say, Australia, and they are complaining about 900 millisecond latency? In REST world, it's super easy to drop a caching layer between your server and the client, because the server is stateless. And modern CDNs providers will let you do it for mere cents for a gigabyte of traffic without changing your code or your internal infrastructure.
I mean, in this case, you can use gRPC for server-to-server communication and provide your client RESTful APIs.
Well, that is certainly an option. But REST is not limited to the client APIs. It has its own place in the backend world as well. Let's take a look. Let's remember, how do we do our cloud deployments usually? Like, we have a couple of instances for availability, and if we need more power, we just add more instances. We pay for them while we need them. When we don't need them, we shut them down, stop paying for them. But what if you're not Google? What if you don't use these two instances 100% 24/7? It means that you're paying for something that you don't need. To address this problem, people use serverless approach nowadays. In this case, your code is represented as a stateless function that takes some external input, executes some logic, and you pay for it only while it's being executed. And REST, being stateless, is a perfect fit here.
OK, so we see that use cases are kind of different, right? So let's stop here before we go too far. What we've got here? The difference between REST and gRPC is visible with naked eye.
Yes, but it didn't stop us from implementing our aggregators using both REST and gRPC. And I'm not talking about code snippets on the slide. I'm talking about the actual code that we wrote, compiled, committed to GitHub, deployed to cloud. And in REST, I started with client polling. In gRPC, Alex used asynchronous streaming. In gRPC, Alex started with writing some IDLs. In REST, I just wrote some controllers and annotations first.
Does it even work?
Well, let's give it a try.
OK, so we have this application.
Yes, we do have this application, which Alex is about to open now, any second.
OK. So what we're seeing here, it welcomes you with generate username, whatever, and here is the actual content. It's either Pokemon or cryptocurrency.
Well, I believe Agor is a Pokemon. Staffel, do you think, guys, it's a Pokemon?
If I click on it, it gives me next.
And Ergo is certainly a cryptocurrency. Articuna, do you guys have any opinions? Is it a crypto or a Pokemon? Well, I'm of two minds myself. I guess it would be cool to be able to vote and choose and see if you have guessed correctly. And to do this, we are going to need to change our architecture somewhat, right? We need to have some new services.
Wait, I'm guessing. Is it Pokemon?
Yeah, no. Let's switch back to
Funfair. Oh, nice, Funfair.
Yeah.
Fair cryptocurrency.
Yeah.
OK.
Yep.
Sure. Let's go back
and see what we need in this brave new world. OK, we're going to need some kind of voting service first, which is going to accept your vote, and it has to talk to content aggregator to see if you have guessed correctly, but it also has to verify that the item you voted for actually exists, because we don't need no fake news here.
And we don't need election meddling either. So voting will pass the vote to a new service called Leaderboard, and Leaderboard will keep track of top 5 guessers, and it will provide them to a client. And client is actually another service, which is called Gateway. And this gateway will randomly choose between gRPC or REST implementations and provide public APIs to our clients. So, and this is how a new architecture looks like.
But with this new architecture, we actually got all these problems we talked about earlier. Leaderboard is an obvious bottleneck. If leaderboard starts failing,
When leaderboard starts failing,
okay, when leaderboard starts failing, then voting service and gateway and clients is going to fail as well. It's a classical cascading failure. And in the rest world, we usually deal with such failures using circuit breakers like histories. What does it mean? It means if the service is failing, we just stop calling it altogether. But we do a health check every now and then to see if it has recovered. If it's still down, we just return some pre-canned response or error message, giving it some breathing room, a chance to recover. But when our health check passes, we restore the communication to it in its entirety.
Okay, and circuit breaker is an awesome pattern, and you can use it in gRPC as well. All you need to do is just integrate histories, for example, with gRPC interceptors, or you can find third-party implementations already available on GitHub. But the world doesn't end up with dead services, and it's even worse to have slow services. Because when your services are slow, they kind of work, but very slow, and your clients complain about latency, and your clients receive timeouts. So, and it's much harder to investigate. And clients are different as well. Some clients are latency sensitive, and some other latency tolerant. And if we use circuit breaker, for example, circuit breakers are triggered by exceptions as well, right? And including timeout exceptions. And what should our timeouts be, right? So, if we set large timeouts between our services, let's say like 1 second timeout, and my client has only 200 millisecond timeout, what happens? When first call takes 50 milliseconds, and second takes 400 more milliseconds, at this point, my client already failed, because its timeout already reached. But my services, they don't know about that. They keep chaining along, they keep calling each other, they just waste our resources. So it doesn't work well, does it?
Let's make a timeout smaller, like 100 milliseconds maybe.
We can do it, but let's see how it affects my latency-tolerant clients. So if my client timeout 2 seconds, and first call takes same 50 milliseconds, second takes 400 milliseconds, at this point we reached our custom timeout of 100 milliseconds, and we return an error to our client. And it will be probably timeout error, even though my client was willing to wait for more than a second, right? So it doesn't work too well either. So to fight such issues, gRPC introduces a concept of deadline propagation. What does it mean? When my client timeout 200 milliseconds and first call takes 50 milliseconds, what should be a timeout from my gateway calling voting service? 200 minus 50, gRPC does the math, and it will automatically apply 150 milliseconds to the next call. And if my voting service is ready to call my leaderboard in another 400 milliseconds, what should be a timeout? Again, gRPC does the math, 150 minus 400. We have no time left. At this point, gRPC will cancel all the calls for this request, and will, with deadline exceeded status code, and it will not even try to make call from voting to leaderboard, because gRPC knows that my client is not interested in the response anymore. So, and when my client has 2 second timeout, it works for them even when services are somewhat slow. So gRPC will automatically adjust timeout based on time already spent. This feature is available out of the box. We don't need to do anything with it. So it will just do it and save my resources.
Well, we solved this problem, but we got ourselves a new one. How do we know the culprit? Because when the client called our service, the call went through a bunch of different services, right? We called gateway, which called voting, which called aggregator, which called leaderboard, and then gateway called leaderboard again. How do we know which one of the services is slow? How do we find the root cause, and how do we fix it?
Well, we can use open tracing solutions. For example, distributed tracing solutions, sorry. For example, projects under open tracing or world-famous Zipkin. So Zipkin sprinkles a pinch of fairy dust over our projects, and voila, we see the whole flow. We see all the services that were called, and we see latency on each stage. We see the flow. So what we did, Zipkin, with Zipkin, we just instrument our code. We report to Zipkin every time we make a request. We tell it what service sent the request, what service received the request, how much time did it take, and so on. If it sounds complicated, don't worry, gRPC already did the hard work for you. All you need to do, you have to find gRPC Zipkin integration. It's available on GitHub. You create tracer. With tracer, you just tell tracer where to find your Zipkin instance, and then just instantiate your client and server interceptors. And these interceptors are actually an excellent example of gRPC ecosystems because they were written not by Google employees, but by external third-party contributors.
Well, with REST solutions, it's even easier. You don't have to write your interceptors. All you need to do is add a couple of dependencies to your project and set up an application properties, your application properties to point to the Zipkin collection URL.
Right, but I see some downsides of it, right? First of all, what if I don't use Spring Boot, or I don't use gRPC, or I don't use Java at all? What about like Polyglot Stacks? What if my services are written in different languages?
Well, that's an excellent question. Let's take a look. We have services that talk to each other, and what we can do, we can put a proxy in front of each service. So the proxy will intercept incoming and outgoing requests, and all communication between services themselves will also go through the proxies. And there are several solutions you can try there. You can do linkerd, you can do envoy, conduit. And now, when this proxy has all the information about requests, they can report it to Zipkin or any other open tracing solutions. And it's not limited to just distributed tracing. This approach, which is called Sidecar proxy, can be used for rate limiting. It can be used for circuit breaking and any other cross-cutting functionality.
Right, but again, there are downsides. Right? First of all, my application doesn't know about this tracing, so it's nearly impossible to customize data I send to Zipkin. And second, it probably incurs performance penalty because there is an RPC I have to make. So it can be, an issue for my latency-sensitive clients. Yeah,
but also it's totally indifferent to your language or framework. It works in Polyglot Stack, as you actually asked originally, and it requires no code changes on your side.
Right, but okay, so regardless of the solutions you use to report your response to Zipkin or any other open tracing solution, you can have this latency distributions like that, and here we did exactly that. So, and as you can see, we have gateway calling voting calling content, and it calling leaderboard. So we have this microservice mesh, and it can send Pokemons, it can send cryptocurrency, it allows us to vote, it has some fault tolerance. So who wants to try it and test your cryptocurrency knowledge? Get your smartphones ready. Mykyta is going to tell you what to do next.
Okay, so I have this application open, and Alex is going to open this application on the big screen to showcase you what you can do with it. And okay. I'm going to use it for a second now.
So open your smartphones, connect to Wi-Fi.
Yeah, I did.
Okay. So here's how our new application looks like.
So you see we have two buttons called Crypt and Pokemon. And if you think that Jinx is a Pokemon, you press the Pokemon button.
Pokemon?
Yes, Pokemon. And if you think that Komodo is a crypto, you press the Crypto button.
It doesn't sound like crypto.
Well, it does sound like crypto to me. Well, I don't know. We can guess soon, right? Because we have our votes recorded, because they can be seen here in the leaderboard. And my name is Smashing Darwin. And I'm not doing too well here.
Yeah, you have to do better. Let me reload it.
Yeah, okay. I got to the top of the list competing with Alex. So yeah.
So you don't know cryptos, as I.
Yeah.
Okay. Anyway, you probably need link, right, to the application.
Yes, there is a link.
First of all, before we give you a link, you see there is a generated username. So this username is actually the way how we.
No, that is you.
You is really you.
Because we are going to have a competition, because we have these awesome prizes from Google and Roku. And two leaders, one in each category, is going to get these prizes. And if you find yourself a winner, please take a screenshot of your application of the web page, or just keep it open so we can know that you is really you when you claim your prize.
Right.
Okay, and now to the link.
Did you guess already what's the link?
And the link is
No.
gRPC res.com. Yeah, it's gRPC res.com. Open your phones, open your laptops, go there, and let's try to vote. And while you're voting, actually, let's go ahead and take a look what happens under the hood.
Yep, we need to go back. First of all, check. Oh, yes, I see more people now. Okay.
Okay, fine. Yeah, the fight is up.
Okay, what we see here? Here's our like distributed tracing UI.
Yeah, just reload it.
Reload. I have to reload.
Disable auto reload. Enable auto reload.
Oh, nice. Now I see your votes right here. So if I click, every dot is actually a vote, and every dot is a request. If I click on this request, it gives me distributions of latencies.
Yes, but that's just a gRPC votes because you filtered for gRPC spans here in your Google tracing solution. Let's filter for REST. And
for REST, I know. Okay, yes. Let's filter span with REST voting, right?
Yep.
No, I misspelled it again. Every single time.
You just don't like REST, I know that.
Okay, REST voting. Oh, the response. Oh, wow. Nice. The distribution is interesting for the REST. I mean, if I click on the REST request, it gives me the same distribution, right?
Yeah.
Same, but different, but still the same.
Yeah, it's just different services, but you can still see the whole hierarchy. Let's check the leaderboard. Let's see what's happening there.
I see a lot of dots here. It means like people are competing. So
which is good.
That means that we have new leaders we can have.
Yeah, Ace Blizzard and Epic Pestilence. I love the nickname, by the way. So are the leaders, but the fight is not over.
Prize just for username.
Okay, you see, it's like the rest still get a chance. So keep it up, keep it up.
Okay, sure. And but we were talking about some fault tolerance, right? But how do you test fault tolerance?
Yes, how do we test fault tolerance? We break stuff. Everybody is familiar with Siemens Army, like Chaos Monkey, Latency Monkey by Netflix. So I'm going to play a role of Latency Monkey. So, and I'm going to add some latency to the leaderboard because it's our bottleneck, right? To one of the leaderboard APIs. Right.
So Mykyta has this magic command that adds 700 millisecond latency to WOD API to record WOD API in leaderboard. And why that important? Because our client timeout is 500 milliseconds. So the latency Mykyta introduces is more than clients can tolerate. So let's see what happens.
Latency Monkey is on in 3, 2, 1, broken.
Okay, nice. What should we check? Okay,
yes,
first of all, let's check if application still works. I still can get next item. Oh, nice. Yes. So that means that even
can you vote?
Let's check. I probably can, but
it depends.
Is it?
Yeah, just click it, right?
Okay, and I get next item. So it means when one API is slow and kind of broken, doesn't break entire system, which is nice. Let's see what is here. So leaderboard still shows us some results. They can be outdated because like WOD API is kind of broken. But let's see. But I mean, it still receives WOD.
Well, yes.
From time to time.
Because occasionally.
We will show you why.
Yes.
So
reload it, auto reload.
You think I need to?
Yes, I believe I need to. You need to reload this thing, right?
Let's just click and see. Okay, I click and now we see, as you can see on latency distribution, that this request didn't even call leaderboard.
Yes, because it's the REST solution. And what do we do for the REST solutions to handle the failures? We use circuit breakers, right? We don't call it at all, but you can still see several high latency calls.
Yes, let's click on this high latency calls.
Yep, no, the higher one.
The higher one?
Yes, the higher one.
Oh.
Yeah.
No.
Yeah.
It's the content.
No, this one.
Let's reload.
Oh, yeah. And see, this one still calls leaderboard because we have to do our health check. We need to make sure it's up, right?
It's not.
Well,
but we still,
yes, we're trying. We're doing our best. Let's check gRPC solution now.
Okay, so in gRPC, I didn't integrate it with Hystrix. I just rely on default, out of the box, deadline propagation. So let's see what happens. In gRPC, you see it like all the requests now take 500 milliseconds, right? You can see it on right here on the top.
Yeah, you can see exact time when we broke things.
On the top right, yeah, you can see exact time. So, but if we click on any of this request, what we see here that like it was rejected with dead unexceeded status code. The status code you can see on the bottom right. Bottom right is dead unexceeded. But the interesting part is here. Then when actually leaderboard was called, this call was cancelled. You see, the status code is cancelled. It was cancelled after 371 milliseconds because it's a time left to call leaderboard, and so even though the leaderboard call itself took like 700
but
milliseconds.
I guess now we can wrap up our competition. Let's check the leaderboard, the actual stats results, and declare the winners.
Sure. I need my phone
Yeah.
to record the results. Okay.
So Gnerly Shining and Epic Pestilence are the winners.
So
guys.
your favorite username still gets Rocco.
No, Gnerly Shining actually got ahead of Ace Blizzard, so it was a fair competition. So guys, girls, ladies, gentlemen, please find out us after the talk if you are the winners, and don't forget to make a screenshot or just keep your application open.
Okay, so yeah, let's go back to our slides. You're not the winner?
Too bad. So, yep.
Come next time. It's fine. Okay, so
the whole code of our demo, which is about a dozen of different services, can be found on this GitHub repo. Come and check it out if you're curious how we did what we have done. And here are the links which you can use to learn more about gRPC and REST. When we publish our slides, you can use the same link, grpc-rest.com, to find the slides, find the links, and learn more about this stuff. And also, I would like to thank this guy without whom the demo wouldn't be even possible. He wrote a UI for each service and made our demo. Thanks, Evgen.
Thank you, Evgeny. So, Evgen, I hope you hear us. And okay, on slides and demo, we saw that gRPC is best fit when you need streaming and performance.
But REST is really good when it comes to resource management, and it's really simple.
And okay, so both solutions actually can handle the most common issues in microservice universe.
And you can even use them together like we did in this demo. And what are we trying to say here?
I'm here. No.
Yeah,
we're trying to say probably that if REST is an architectural pattern, right, and gRPC is a library and it can do unary calls, you can implement REST over gRPC.
I understood all the words, but they just don't make any sense. It seems like it's your jet lag token.
No, I mean, we can.
Like,
but yeah,
I guess we can.
That's not what we were trying to talk. We were trying to see if there are more cryptocurrencies than Pokemons.
Okay, just stop there. You may have gotten an impression that the tool that you choose actually defines the architecture of your application, but that's not true. Every tool, gRPC and REST, can solve virtually any problem in the microservice universe. The difference is the amount of effort and time you have to spend to solve your particular problem in your particular use case.
After all, tools make the master, and we hope that after this talk you have a better idea what tool you might need to mine your cryptocurrency. So if you have any questions, we probably have...
Yes, we have
1 minute to answer your questions.
So one question, we can take one question, and then winners can claim their prizes.
And, okay.
Okay, the gentleman there.
Search. Okay.
How does it work? This native channel is not really good with making blocking calls. It will block all of your requests at the same time.
Sure. Yeah. So the question was, how does it work with how blocking clients in gRPC work with native channels, right? So first of all, when I created a channel, I created gRPC channel, not to be confused with native channel. It's a like abstraction on top of native channel. So it will not just like use native channel. It's like an abstraction on top. So blocking clients will block the thread, but it will not block the like single native thread. If you're asking about that, it will not call this event loop thread. But it's still not the best idea to use blocking clients.
Yeah. Yeah, native will keep running, but the whole application is probably will underperform.
It will not block event loop, right? You have questions, well.
I was wondering if gRPC supports the concept of back pressure.
Yes, it does. The question was, sorry, I will repeat the question. The question was if gRPC supports back pressure. gRPC does support it, and it's called flow control in gRPC. We just didn't have time to cover it.
OK, so the time is up.
Thank you for coming. And
you can find us in the hallway. If you have more questions, we'll be happy to answer them. If you like the talk, please vote for us. If you have feedback, please leave it in the application as well. We really appreciate this. And again, thank you for coming. It's really good to see you all here.
OK.